Question number 1, what produces the energy in the sun?
Fusion.
Fusion. Good. Any questions about that? Okay. Number 2, what will happen when the sun stops producing this energy?
The supernova?
Nah.
No die.
It will slowly just
Get bigger.
fade away. What?
Yeah.
I'm sorry, what did you say?
Does it not get bigger?
Well, when it stops all fusion, essentially the star dies. And what will be left of our star at that point will be a white dwarf and a planetary nebula. The planetary nebula will fade off into space. The white dwarf will slowly cool down into something like a black dwarf until it gives off no heat, but it just dies. Star must be doing fusion to continue producing heat, etc. Okay? All right, number 3. How does matter / antimatter pose a problem if you don't believe in a creator?
More matter than antimatter in the universe.
More matter than antimatter, and they should be
Equal.
equal. Good. Okay. In the picture above, what is Y? Gamma rays, right? High energy photons. What is E+?
Positron.
Positrons. What is V? Neutrinos. So, just in case, this is gamma rays. Right? E plus equals positrons. Neutrino is V. Okay. Yeah, that's number 6.
Never mind. Matter than.
You good? Take your time. Okay. Number 7, what happens to positrons after they're formed?
Canceled out by electrons.
Yeah, no,
They
look,
collide, but
you don't have to tell me exactly some specific formula. If you tell me that, hey, they crash into an electron, or hey, they get annihilated as they crash into an electron, or hey, they become light, as long as you convey to me that you understand, we're good, okay? Makes it hard for me to grade, but you know, it's easier for you. Number 8, what happens to gamma rays after they're formed?
disperse.
What's their ultimate end? They leave, right? They go out as light. Okay. Number 9. Any questions about number 8? Sorry. Those gamma rays, the reality is they actually bounce around for a very long time and hit off things and transfer energy, but ultimately they leave as light.
Yeah. Would you accept get pushed out?
That's fine.
Alright,
They don't get pushed out. They, they want to go out.
alright.
They're trying to, they're flying around the speed of light, right? Yeah, pushed out wouldn't technically be correct.
Oh,
Okay.
Yeah. Crashes into
Number 9, what happens to neutrinos after they're formed?
You leave.
Yeah, they fly it. Now these don't bounce around, they're gone. Right? They don't interact with the particles.
They fly.
They fly away, that'll work. I'm gonna stop right now because I've seen a lot of like kind of side things, like maybe somebody missed something, they're trying to catch up. I don't want to go on and you still need some stuff. So on those first 9, does anybody need anything repeated or explained?
Can you repeat 7 again?
Yeah, 7. What happens to a positron after it's formed? Remember, I'm going to teach it, I'm not just going to explain it. This thing has a positive charge, right? And it's surrounded by all these electrons with a negative charge. It's just 2 magnets, right? So they're going to hit each other, they collide, and off comes 2 gamma rays.
Crash into the electron.
That's exactly it. They crash into an electron, and then light is produced. They annihilate them, right? Okay.
Did you not do a 9?
Number what?
Number 9.
Number 9, yeah. So neutrinos. Now, you got to remember, neutrinos are happening in this very first step when 2 hydrogens or 2 hydrogen nuclei are slamming into each other, right? And a positron gets kicked off. That's how the charged part happens of a proton becoming a neutron. but the neutron has slightly less mass, just slightly. The difference in mass is the mass of one neutrino and one positron. So this little tiny bit of mass comes flying off almost at the speed of light. It has no charge. It passes right through. Remember that video we said you're getting hit by like trillions and trillions of neutrinos right now. Passes through your hand, right? But it kind of doesn't. Some of it does, but some of it doesn't, right? The parts where it does, the X-ray is black. The part where it doesn't, the X-ray is white. That's how we can see your bones and stuff, right? Wherever it hits your bones, the bones absorb it. Well, neutrinos, you couldn't do an X-ray with neutrinos. They would all be black. They're just passing right through. Okay? That was probably way more information than you just wanted, but, you know, hopefully you understand it. So, you feel good with that one? Awesome. Any more on those first 9? Okay, let's go to 10. True or false? The total mass of all the hydrogens required for the proton-proton chain is equal to the mass of the hydrogens and the heliums found at the end.
False.
It's false. So actually have 6 protons going in. Okay? What you come out with is a helium nucleus, right? So 2 protons and 2 neutrons. And then you also have 2 other protons that get kicked off. So the question is, hey, is this mass the same as this mass? And that answer is no. Right? Because we've lost a positron and we've lost a neutrino. And these things both have mass. Right? So the way this is formulated, this is less than this. Now, had I asked if this was the same as this, that answer would be yes. Okay. We feel good on 10/11 because it got split up and it shouldn't. So number 12, if the final mass is greater, where did it come from? Was the final mass greater?
No.
No, it's lesser, right? So if the initial mass is greater, where did it go? We actually already answered it, right? It becomes a positron and a neutrino. Okay.
So what would we put on number 12 though then? Would it just be like NA or?
Yeah, exactly.
I ended up putting energy converts to mass.
Yeah.
No, not applicable.
It's a great hypothesis, but it's not actually what happens.
I thought it was not connected. I didn't know it was connected to the last
Fair
one.
enough, fair enough.
What'd you say, heck? Just NA on that one?
Yeah, number 12 is not, it's just not there. There's nothing there to write. Number 12 and 13 both relate to question 10, okay?
Okay.
And then number 13, if the initial mass is greater, where did the mass go? Positron and a neutrino. Positron and a neutrino. If in any way you're feeling discouraged right now, I would like to encourage you that this is probably the hardest test you'll have in here. And it's still not that bad, right? So, you'll be fine. Do we need any more explanation on that? Okay. All right. Number 14. Which is greater, the mass of a proton or a neutron? A proton has greater mass. Now, why does a proton have a greater mass than a neutron?
Neutron loses a neutrino and loses its mass to a neutrino, and the positron is created.
That works. That's one way of saying it. Another way of saying it would be that I would have to add the mass of a positron and a neutrino to get a neutron. That would work, wouldn't it? No?
I just don't really understand it, I guess.
Okay, let me just do this, okay? This is a proton, okay? This is a neutron, okay? I can convert from one to the other. If I want to turn this into this, I've got to do something with its charge, right? I've got to give it a positive charge. What particle's going to let me give this a positive charge? Not a proton,
Positron.
positron, okay? That's this little guy right here. And this has mass. It actually has a lot more mass than the neutrino does. And it's got charge, right? When I add these two together, I'd have the positive charge that I want. I'd be very close to the mass that I want. But it wouldn't quite be there. It'd be like, you know, some little sub-percentage off. And so that little tiny bit of mass is going to be found in this neutrino. Okay? Most of my mass, most of my matter is going to be found in the neutron. It's neutral, has no charge, it's pretty big. When I add this is going to add a whole lot of charge, right? And it's going to add mass. This thing, no charge, and it's got this little teeny tiny mass. When I add these three together, you get that. And the opposite is also true. If I took a proton and I subtracted a positron and I subtracted a neutron, or I'm sorry, a neutrino, I would get a neutron. The charge is coming exclusively from the positron. The mass is coming mostly from the positron and a little bit of, can I make up just fake numbers? Just fake numbers to help us out, okay? This has an atomic, and I could look up the real numbers, but you know, you don't want those and they're crazy, tiny, and difficult to work with. This is 1 AMU, okay? This must be something slightly less than 1 AMU. Let's call this 0.9 AMU. It's not, it's like 0.99, you know, it's very, very close. But for right now, we're going to call this 0.9, which means these two combined must be 0.1, right, for our hypothetical. This is not real, I'm just trying to demonstrate it. This is going to be like 0.1, right? The whole thing is 0.1, but I'm going to have to go and I'm going to call this like 0.09, and I'm going to call this 0.01. When I add these together, what do I get? 0.1, and when I add 0.1 to 0.9, I get 1. So that's it. Mathematically, and again, these are not real numbers. Just trying to demonstrate. Like, this is a whole lot bigger than this. But this matters. And as far as charge, this is carrying all of it. Okay? So 0.09 plus 0.01 equals 0.1. 0.1 plus 0.9 equals 1. Right? And a positive charge. And I can go in reverse down here. I can go 1 minus 0.09 minus 0.01, and I will get 0.9. Okay? And if at the end of the day that still doesn't make sense, it's going to be like 3 or 4 points out of the whole class. You'll be okay. All right? All right. Well, let's roll on. What's next?
What do we write?
Which one are we on?
14.
14. Which is greater, the mass of a proton or a neutron? Well, what's the answer?
Yeah, I know, but where to write?
Yeah, so the answer is a proton, right?
Yes.
And the reason is that you would have to add the mass of a positron and a neutrino to add up to the mass of.
If we were to just write that down there, would that be good?
I'd probably be happy with that.
Okay.
Yeah, if you said this equals that plus that plus that,
I
I'd
was-
be stoked.
I was just wanting something less work.
I might come high five you. I might just get so ecstatic you just can't tell. All right. Number 15, hydrogen atoms are positively charged. What causes them to get so close? In other words, how does the first step of nuclear fusion ever happen?
Gravity?
Gravity.
Weak nuclear force?
Speed.
Mass.
Speed. All these, gravity, I shouldn't have said it's wrong.
Mass.
It's important. It is a huge factor.
Mass.
You you said speed. Yeah, that's
Rotation.
huge.
Heat.
Heat, that's right there. So
Nuclear force?
heat and speed both are reflections of the fact that they have a lot of, say, energy. Yes, and why do they have energy? Well, initially because of gravity. The force of gravity is causing them to squeeze together, heat up and speed up, and they crash into each other. Everybody with me there?
Yeah.
Okay. So all those are big parts of the whole. Why do they get so close? Essentially because they're moving so fast. They have so much energy. I probably talked to you about this. I just wish I had the right magnet. Even if I did, I mean, you wouldn't be able to see them. I'd have to have a camera or something like that. But if I had magnets and we were playing with, just north poles and north poles, if you just gently slid them to each other, they'll get kind of close and then they'll shoot apart, right? But if I slam them hard enough, fast enough, with enough energy, they will crack into each other, won't they? You ever done that? Like really slam magnets into each other? The same poles? What happens? They explode. If you do it fast enough, they explode. Good times. You look like you've never done this before. Well, I don't know if you should or you shouldn't. I mean, it's like $1 at 25 or something at Harbor Freight for like the ceramic. You can just like slam them all day. Can you tell I like magnets? Anyway, so hydrogen atoms are positively charged. What causes them to get so close? It's the energy, right? It's crazy hot in the core of the sun, right? All right. Whew, it's crazy hot in this room. What time is it? All right, doing all right. We're not going to finish this. That's all right. You got an extra day built in? No. All right. Hydrogen atoms are positively charged. What? Hydrogen atoms are positively charged. How can they remain together in a nucleus? So these are actually two different questions, okay? You might not remember that we talked about this. Did it pretty fast. That last question is different than this question. The last question was essentially asking, how is it that I can have the first step? I should have done it this way. How can I slam two protons into each other and turn them into a, what's this called by the way? Deuteron, good. Okay. How can I slam these two things into each other and get a deuteron? The answer there is the energy, right? But then the next one is really, how do I take this and slam another one into it and it holds together? How does that happen?
Use nuclear force?
I'll put a heat and pressure.
This is actually going to be the strong nuclear
Oh,
force.
it's strong.
Yeah. And me being me, if I saw the word nuclear force, I'd probably just, like, I'd be happy that we got there. This is the strong nuclear force. This is stronger than the force of repulsion, electromagnetic or electrostatic repulsion that wants to push them away. But this only works, like the field for this thing is very, very narrow, very, very small. They have to be within the diameter of a nucleus of an atom. You get any further away, it can't overcome the force of repulsion. Okay. Questions about that? You understand it? Great. If all you did was memorize it, that's the answer. Be okay. Get yourself some points. What do the E, the M, and the C in E equals MC squared stand for? E? Energy. M? Mass. C? Speed of light. Energy equals mass times the speed of light squared. we were taking this class at the level of, you know, astronomy for majors, you'd be doing all kinds of stuff with it. We're not doing that. You can skip number 18, I'm not giving you anything like that, okay?
I just squared it.
Hmm?
I just squared it.
Yeah,
Yeah.
that works.
Put in a calculator.
I'm still not doing it. We don't need calculators.
No, without calculator, just wrote the same number, put a square on it.
Oh, well, that's fair.
No idea what I'm saying.
Fair enough. All right. Number 19, whenever matter is created from energy, in accordance with E equals mc squared, it comes from two forms. What are they?
Matter, antimatter?
It comes in two forms. Yes, it comes in the form of matter and antimatter. I'm going to go turn off this heat because it's killing me. All right. Where are we?
20.
You say the princess. All right, Link. Anybody else know that that was from Legend of Zelda?
Legend of Zelda?
Y'all weren't born. That's okay. It was the coolest game ever when you were 10.
Still is.
On the original NES? Probably feels pretty lame. There. What's an anti-electron called?
Positron.
Good. What happens when matter and antimatter collide? I want more than just they cancel out.
Become energy.
Annihilate.
They annihilate and become
Energy.
energy. Good. We're going to do these last three and we'll stop for today and we'll pick up where we're at next time, okay? Number 22, what is a neutrino? Tiny chargeless particle that travels at nearly the speed of light, okay? Tiny. Neutral. And it travels at nearly the speed of light. Alright. What is a gamma ray?
Light?
It's light. Can we be slightly more specific?
Dangerous
Really?
light.
It is dangerous light. We can be better, more specific than that.
Really energetic.
We can be more specific.
The most energetic.
The most energetic. It's the shortest wavelength, highest frequency, most dangerous light. If you just wrote high energy light, I'd be really happy. Okay. If the grades are poor enough and my self-esteem needs a boost, I might even give you credit for light. But if everybody else is killing it, you'll probably lose half a point for just saying light. Tell me that it's high energy light, okay? All right, number 24, what is a deuteron? Can you draw a deuteron?
Yeah.
What does it look like?
The thing right there, I think, lighting.
Yeah, that. Good, that's it. It's a proton and a neutron.
Can I just write H2?
Like 2H?
Yeah.
Yeah, you could. You probably will, won't you? I'll take it. I'll be happy. All right. We're going to stop right there. And we'll pick up there next class and we'll finish up. Okay? Now we can. You'll have a wonderful weekend.